has quite a bit about polar coordinates in it. And if you took Math 175 from me, you recognize one of the handouts, the little booklet thing, because I always give that out in 175. And if you recognize it and know that you have it, then you could turn it back in at the end of class. If you don't know that you have it or where, why, then you can keep it. It's handy to have pictures all in one place of the various polar curves that you work with in some of the problems. So just to remind you about polar coordinates, starting here, there are two independent families that you can use to represent the coordinates of a point, like this one here, in polar form. Because if you think of some point, let's say this point in the corner of the room where the carpet changes, so you can think of the solid color as indicating an axis this way. Think of the plane of the floor as your XY plane, say, as if you were in 3 dimensions. So think of X like that, and Y like this. So then the origin of Cartesian coordinates, Cartesian refers to René Descartes and means the letters X, Y, Z, okay? So the origin of Cartesian coordinates, where the X and Y axes would join, then is where you normally take the pole for polar coordinates so that you can get relationships between the two systems. So if you thought of it that you're what we call the initial ray of polar coordinates, so that brings up the question of the word ray, R-A-Y. So a ray then in polar coordinates is a line segment starting at the pole, which is here in my picture, and going as far as you want to specify, out to some point or out to infinity, either way. Just a second there. A ray, which you take along the x-axis, looking at my picture, as being this line here between the solid and patterned carpet, and this is the pole. And suppose I was going to the point over here that would be 1 and 1 in XY coordinates, so 45-degree angle. So I turn through the angle first, and then if I can walk toward it the right number of steps to get to that point. So that would be like I'm here and I turn through the theta, which would be pi over 4. If this point is 1, 1 in Cartesian coordinates, and then I'd walk the distance that's the length of this ray that's in green, which of course would be square root of 2 because of the law of Pythagoras. 1, 1, root 2. Okay, so the r theta then in polar coordinates would be root 2 and then pi over 4. Notice that what you do is you turn through the angle first, but the way you write it is you write the length of the ray first and the angle second. It's like English spelling. It makes no sense, but you have to do it that way, right? And the reason that there are two independent families here is that you can also do this. You can go back to the pole and turn through pi over 4 and then another pi. So now I'm facing this way, and then I can walk backwards. And so that is minus r, for the same r, which is the length of the ray. So I can do minus r, which would point me like the red, and then you see my backward arrows, so I'm walking backward. So this point is also minus whatever was this r, and this angle plus pi. And actually, you see, you could then put on all the 2 pi additions you want in representing the angle, because 2 pi is the 360 degrees, so you could turn around and around until you collapse from being dizzy with this if you want to. So in a sense, there are infinitely many ways you can represent a point in polar coordinates, but there are the 2 independent families, the one with r and the one with minus r. So that means that there's more than one way that you can write the formula for a curve defined in polar coordinates, and there are the 2 ways you can do it that are fundamentally different. In other words, they'll give you identical graphs and the calculus is all the same, but you can't get from the one formula to the other by algebra or trig identities or something, because they are fundamentally 2 different families. And that's what I'm talking about on the front page of your set of notes that you just got. You see, equivalent polar equations have the same graph, and then there is this symbol that's a kind of a wiggle. I guess you call it a tilde if you want the technical word. It means the graphs are identical, even though the equations may not be interchangeable in the sense of trig identities or adding fractions or something. So r equals f of theta then is equivalent to minus r, and you could either use theta plus pi, like I did here, or you could come around this way, which would be theta minus pi. And of course, theta minus pi plus 2 pi is theta plus pi. So that's covered with the idea that you can put on all the 2k pi you want for k any integer, you see, and you're back where you were. And we don't need to read through all of this, but it's a handy rundown of various things that are true about polar coordinates. But one thing that's worth noting, at the bottom of the page, I talk about tangents at the pole. So if you have your polar, your formula for your graph in polar coordinates, the f of theta, if you set that equal to 0, then that's where r is 0 and you're at the pole. And there typically will be some trigonometric equation then, some function of theta equals 0. And if you remember your Math 144, Math 147, or trig in high school, solving trigonometric equations, there may be several solutions. So for instance, turn to what would be page 4, the back side of the second sheet of paper. And you see these things that look like flowers, and some people call them petal curves with a T because of the flower petal, and some people are more romantic and call them rose curves. But I really think they look more like daisies than they look like roses. Well, anyway, for instance, look at the one on the left. Any coefficient A, sine of 3 theta. So if you set sine 3 theta equal to 0, what you're getting will be various angles, and if you have r equals, if you're at that angle, then what you're doing is going from the pole out at that angle. So that would be a ray, which is, remember, the word ray refers to a line segment from the pole going as far as you want to specify. So you'll have, as you see there, a ray at theta equals 0, another one at pi over 3, another one at 2 pi over 3, another one at pi, another one at 4 pi over 3, and another one at 5 pi over 3, and then you start repeating yourself. And each of those is tangent to one of the petals as you come in at the pole. And as I show you there with my handwriting, if you set sine 3 theta equal to 0 and start looking for solutions, you see the first one you'd have is pi over 3, because 3 times pi over 3 is pi, and sine of pi is 0. And then you'd have one at 2 pi over 3, because 3 times that is 2 pi, and you'd have sine of 2 pi, which is 0, and so on. So I have the solutions listed under the left-hand picture, and then the center lines of the petals are halfway between the two successive tangents. So those would be, you can identify those, pi over 6 and so on. So knowing all that, then you can make the sketch. So this, and I've done the same sort of thing with sine of 2 theta, where you have 4 petals, and then it turns out if it's sine or cosine of n times theta, where n is a counting number, if n is odd, that's how many petals, like 3. If n is even, like 2, 2 times that is how many petals. And that's true with either sine or cosine. The difference between the sine and the cosine flowers on the next page is one graph is rotated compared to the other. You see the sine 3 theta as compared with the cosine 3 theta. The sine 3 theta is rotated, is the cosine 3 theta rotated through 30 degrees. And then you can look at the sine 2 theta and the cosine 2 theta, and the sine is the cosine graph rotated through 45 degrees. Well, you can look through this as you need it, but we need to know something about polar coordinates, or remember something about them for this section. So now come over here, and that goes with the other sheet of paper you have with the area in polar coordinates. And so this picture is essentially what's on the sheet of paper you have. And so what I'm thinking of is I have some region in the plane, and I want to set up an integral to get its area. And I can do this if I construct a Riemann sum, which is made of tiles like this one that's in the brown in this picture, or like what is in the handout that you have, where I've written the word tile. And so what you can do to set up a Riemann sum for this is you can say you're thinking about this portion of the plane, and you can draw rays. Remember, a ray is a line segment that starts at the pole and has a length that you specify. So each of these is a ray, and so would be the x-axis and the y-axis in my picture. And then I'm subdividing the angle theta through here, as we usually do it with these upper and lower sums. I'm making equal divisions. And then I can draw arcs, which in this case these are all arcs of the circle, and I can have these equally spaced. In other words, I can think of a radius like this, and I can divide that into 6 parts or whatever, like as I have. So then I have I as identifying the arc here. I, in this case, 0 would be back here at the pole, and then 1 through 6 as I've drawn it. And then I can draw the rays, which would be the j's, and then the ray with j equals 0 would be along the positive x-axis. J equal 1, 2, 3, 4, 5, 6 would be along the y-axis as I've made the drawing. And obviously this can be any number you want to choose. So now what we need is a way to represent the area of a representative tile. You see, this tile then would be subscripted I, which would be, say, the arc on the interior edge of it. So say this would be the tile where I is 3, and then where J would be 3 also. 1, 2, 3. So this would be the tile that's indicated with subscripts 3 and 3 in my picture. And so this one would be 3 and 2 and so on like that. So you can set up a pattern in this way. And then what about its area? Well, you see, going from the pole, you have an outer radius, the outer edge of the tile that's in the green in my picture, and a blue radius for the inner edge of the tile. So the green corresponds to capital R and the blue here to little letter r. So we have the formula that for a sector of a circle, if the angle in here is d theta, between my thumb and my fingers, say, then 1/2 the squared radius to the outer edge times d theta would be your differential area. Why is that? Because if the angle is 2 pi, 1/2 r squared times 2 pi gives you pi r squared, and that's a circle. So that's based on the area of the circle being pi r squared. So therefore, we could say for the sector that's where the green is the outer radius, that's capital R. So 1/2 capital R squared d theta would be the area from the pole to there. then for the inner edge, that's little r, that area is a half little r squared d theta. So the difference is the area of the tile. And then what you can do, d theta is a common factor, and then so is the half, and then you have the difference squares, big R square minus little r square, so you can factor it. One thing that's guaranteed in a math class, if a math teacher can ever think of some way to get to factor the difference of two squares, you're going to get that. Guaranteed, you see. So here it comes, here are the factors. And then this half with the sum is your average. So that gets you the R to the midpoint of the tile as you're looking from inward to outward, okay? And so you have an average, so you could put a bar on it for average. And the R bar then would be the black, you see. And then as you go to more and more of these, treating this as a differential, your difference in R, big R minus little r, would be dr, and then the angle is d theta. So your area then is the limit of your double sum, where you're summing from pole outward, so that's taking care of the dr, and from start to finish, and that takes care of the d theta. So the j goes with the d theta, and the I goes, as I've drawn things, with the dr. So I have delta Ri, delta theta j. So that's, if that common limit is defined and is the same number for all possible ways that you make your subdivision, then that common limit is what you call a double integral using polar coordinates. This is the same old Riemann sum game of Math 170, changed to polar coordinates and working in the plane. So the normal situation, if you think of your sheet, the XY plane, Cartesian plane, and then if it's something where the symmetry of the curves is better suited to polar coordinates, knowing how the picture looks, then you have to figure out how to write the boundaries as polar coordinate curves. And if it's part of a circle, that's pretty natural, because the equation of a circle in polar coordinates is just simply r equals some constant. R equals 1 is the unit circle, say. But if your edges are lines, then this is more tricky. And those are the problems that where we're going to focus our attention primarily. We'll start with 9. It's top half of a circle. So these pictures go with this problem. Y's, the green arrows all start at y equals 0, which is the x-axis, and they all go to this half circle, top half of the unit circle. And then the projection of our region on the x-axis is minus 1 to 1, minus 1 to 1. So our region is the half circle. Okay. And you notice that this is just an area. As long as it's just dy dx or dx dy, or the r dr d theta in polar coordinates, you're just getting the area. So you know the answer is half of the unit circle, which is, well, the unit circle, the area is pi radius square, where radius is 1, so that's pi. and this is half of it. So you know that's where it's going to go. But looking at it as an integral, you see the replacement drawing, it's the same half circle, and thinking of my picture at the far end of the room, I have then these sectors of a circle, these fans coming out from the pole, and I have my little tile there, okay? So what's in blue and brown here, that's like this piece of the fan over here. If you think of the whole picture, looks a little bit like a fan. And you have your sector coming out, and you have the thing outlined in blue back at that end of the room, and you have your tile. So make the connection that way. So the inner curve here is 0. Because you're going clear into the pole. And so that's F1 of theta, which is R equals 0. And the outer curve is this arc of the circle, that's R equals 1. In this case, if it's arcs of circles, you see your formula is a constant. But a constant is a function of whatever variable you want to think you're talking about. You take any value of the variable, and what you pair with it is that constant. In XY graphing, y equals 2 is a horizontal line. Name any x you want, 2 is your y value, but it is a function of x in that sense. Okay. So the limits on theta then are 0 to pi, because it's the half circle. So your inner integration is r dr, 0 to 1. Outer one is d theta, 0 to pi. Okay, half r squared, 0 to 1 is a half. And then integrate d theta, you get theta, 0 to pi, so you get a half pi. So the section 15.3 is about finding area in polar coordinates, and the point in that section is like this, just simply that if it's dy dx or dx dy, when you do the integral, you're getting the area of your region. So my focus here today is on 15.4 because in that sense, 15.3 is kind of obvious. So look at 13. Now this is more challenging. The reason it is that your region is triangular, as you see, and that's not so natural to polar coordinates to write the polar equation of a line. Well, you might be thinking, well, how do you do that? Well, I'm about to tell you. Okay, so here's our problem. Notice this one is not just the area, because you have a function in here. So the region still goes with the limits and the order. In other words, x runs from 0 to x equal y, so that's horizontally because it's x. They're all starting at x equals 0, that's your y-axis, and they're all ending on the line where x equal y, which is also known as y equals x. So they're going like this, and then the projection on the axis you name the second in Cartesian form is 0 to 6 back here. Okay, so the challenge is to write the equation, especially of this top line, in polar form. You see, this line is, if you think of your pole down here, as you would, this is a ray, that's actually at a 45-degree angle. So the role of this line is to give you the limit of pi over 4 on the theta when you get over here to our theta form. And the role of the y-axis is to give you the upper limit on theta. If you think of theta where you're going as I'm turning the stick like that. But the problem is that your sectors from the polar coordinate fan all end on this horizontal line. Well, this is the line y equals 6. Y, you see, so that if you've taken your pole at the origin, then you get these connections between polar and Cartesian coordinates, which you should have been told about in Math 143 or 144 or 147, something like that. And so what we have is y equals 6, and y is r sine theta. So therefore r, which is your function of theta, defining this boundary in polar coordinates, is 6 over sine, so it's 6 cosecant. So that's what I've tried to indicate with my picture down here. See, this is your same region that this is. This is one of these sectors, one of the little tiles, and they're ending r-wise, where r is the distance out from the pole. They're all ending on this horizontal line. Again, the role of the x equal y and the y-axis is to get your limits on the theta. And the challenge in here is to get your limits on the r in terms of theta. So we also have to rewrite the function here in polar form. If you're changing the dx dy to r dr d theta, you can't leave the x alone either. So you also change the x because of this into r cosine theta. So then this x is r cosine theta, dx dy is r dr d theta. You always go in that order because your limits on your boundary curves like this are r in terms of theta. See, 6 cosecant theta. So then the r is going from 0, because this is in here at the pole, to 6 cosecant theta. So that's the tricky part, seeing that that's where the r goes. Okay, so notice you do the r first. So you have r squared in this problem. Cosine theta comes later. You have the r squared dr. Okay, so that's going to be r cubed over 3. And then you have the cosine stuck out at the side with the d theta. And so you put your 6 cosecant theta in for r cubed. And 6 cubed is 216. This 3 is that 3. And you have the cosine from the x, and then cosecant is 1 over the sine. So instead of writing cosecant cubed, I wrote it as 1 over the sine and wrote sine cubed in the denominator. The reason for that is that if you, see, I'm going to do a u substitution. If u is the sine, du is cosine d theta. So it makes an integration that we can really do in the sense of U substitution type things. That's why they put the X in the problem, to make a problem that you could really do pretty well. So now I have du on top and u cubed on the bottom. And so then I have to change my limits on theta into limits on u. So u is sine theta, theta is pi over 4, and u is sine theta says u is root 2 over 2, or 1 over root 2, whatever you like. And then at pi over 2, and u is sine theta, then sine pi over 2 is 1. So 3 into 216 is 72. You integrate u to the minus 3 and get u to the minus 2 over minus 2. And then 1 over root 2 to 1. Notice this is 2 into 72 is 36, and the minus is there. 1 over u squared, and these limits, and work that out and you get 36. So what you'd be thinking, for example, if this were a mass density sort of thing, where the density varied with x, then this would be a computation of mass, something of that kind. You'd have to give a physical interpretation. First of all, it isn't area because of this factor. And then you have to say in physical terms what this function is supposed to be. It could be charge, and then this would be the total charge on the plate, something like that. Okay, so then the next one starts up here. This one is not a trig function one, so let's skip over this for a moment and keep going with the ones that involve the trig functions. So skip over that for the moment. Come over here. There's number 15 and number 16 that are the trig function ones. So let's do those and then go back. So if you look at 15, this is an area problem. See, it's dy dx. And of course, with these that are area problems, once you figure out what the region is, if it's a geometric figure like a triangle, you can figure out the area, and so you can get to the answer that way as a number, but that's not what they want you to do. But you can certainly check your work that way. So what we're told is that in the y direction, we go from y equals 1, which would be this horizontal line up here in red, to y equals x, which is the line that makes the 45-degree angle. And then that the projection of our figure on the x-axis is from 1 to root 3. So this would be the projection down here in red. So that tells us that our region is this triangle up here where the green is. And so you could figure out a half base times height, where the base is root 3 minus 1, and the height is 1 up here. Let's see. No. over here at root 3. So this is root 3 minus 1 that way. So the region is a triangle. Area is a half base times height. So it's a half. The length of the base is root 3 minus 1, and the height here is root 3 minus 1. So you could get the answer that way, which matches what you get if you do the integration. So coming back to doing the integration, you see your problem now is that you are using the ray from the pole to this point to determine the angle alpha. So your sectors are in here, and they're starting back here and going, so they're going from the red here to the vertical over here. And you're using this edge, which is the line y equals x, so that's a 45-degree angle to get your beta. For your alpha, you see your tangent of alpha is the height, which is 1 over root 3, which you can rationalize, and that goes with 30 degrees. So your limits on your angle are 30 degrees to 45 degrees. 30 degrees to 45 degrees, like that. So then, looking at your vertical line, well, let's see. Look first at the base here, because you're thinking about second here. So you're thinking about a thing like this. You got your sector like that, and then your tiles would be in here. Okay, so your base here of this triangle is where y is 1, so r sine theta is 1, so r is 1 over sine, which is cosecant. Let's see, r equals cosecant, and my arrow goes to this, which is the same as that in that picture. And then the other end is the vertical line at x equals 3. So if x equals 3, x is our cosine theta, so that's root 3. I meant to say root 3. And then the r is root 3 over cosine, which is root 3 secant. So we're going from cosecant here to root 3 secant there. So our area then, r dr d theta, is from cosecant, which is that, to root 3 secant, which is this side. Or over here, it's from the red to the green here. And then the angle is going pi over 6 to pi over 4. So again, you have a half r square, and then put in your limits, root 3 secant and cosecant. So when you square, you have 3 secant square minus cosecant square. Well, the derivative of tangent is secant square, so when you integrate this, you have 3 tangent. And the derivative of cotangent is minus cosecant square, so when you integrate, you get cotangent. And then you put in your limits and work that through, and you get the same thing as if you simply did a half base times height for the area of the triangle. So you see, these things can be more tricky if you're forced into boundaries that are lines which don't naturally curve like polar coordinates, but you can do it. Okay, look at 16. So this says that the x's are running from x equals square root. So x squared is 4 minus y squared. So x squared plus y squared is 4. So the x, this inner boundary is really the circle. Well, that's a lot easier to change to polar coordinates. The circle with radius 2 is just simply r equals 2 in polar coordinates. R equals a constant graphs to a circle, where the pole is the center of the circle and the constant is the radius. And, or at least the absolute value of the constant is. R equals minus 2 would trace a circle also. What you'd do is you'd turn through the angle and walk backwards to your circle, but it would trace out the same circle. So the radius is going to be the absolute value of the constant if the graph is r equals constant. So that's going to be the inner graph here. And then as this is given, you see the x's are running from the circle, the arc of the circle, which is where I'm pointing with the stick or trying to, horizontally to x equals y, which is the line y equals x. See the red arrows. So they're doing what this says x is doing. And then the projection of the region on the y-axis is from here to there, from root 2. Notice this point here where the line y equals x crosses the circle is root 2. Because what do you have? You have x squared plus y squared equals 4. Square root of root 2 is 2 plus 2 is 4. So the root 2 is the y coordinate of this point. So this is the bottom of the figure for which you try to get the area, and the top is up here at 2. So your inner curve for these sectors, like in blue, would be the arc of the circle, and your outer curve is the horizontal line. Y is r sine theta. So r sine theta is 2, so r is 2 over the sine, which is 2 cosecant. So r then goes from 2, which is your radius of the circle, to 2 cosecant. And then your angles run from 45 degrees, y equals x, to 90 degrees, pi over 2. Okay, so again, you have a half r square, put in your limits, and you get 4 cosecant square minus 4. Then you can factor the 4 and divide by 2, so you get a 2. So you have cosecant square minus 1. Okay. Derivative of cotangent is minus cosecant square. So the integral of cosecant square is minus cotangent. And from minus 1 you get minus theta, and you go pi over 4 to pi over 2. And if you work that out, you get this? Well, you can check by using your head, see, because what is your region? It's this triangle, the big one, minus this much of the circle. In other words, the triangle goes from the pole out to there, and you can take away this part of the circle, and that would give you the difference. Okay, the triangle's a half base times height. The base over here is 2, and the height is 2. So half 2 times 2 is 2. And what you're taking away is 1/8 of this circle, for which the radius is 2. And so 1/8 of pi r squared. So you do that and you get the same answer. So these are rather interesting problems, I think. Anybody got a question on it? One thing that you always want to do with math or anything else, but I think especially with math, if you have a problem, see if you can think of some comparatively simple way to check whether what you're doing is right or what you got is right. And I think it's always generally a good plan in life with anything is sit down and think a minute, well now does this really make sense? Of course, if you did that with what is the inundation on television with the politics, none of it makes any sense of what they say, but that's another story. Meanwhile, back here, the problem 20, we'll get away from having to write lines in polar coordinates at least. Notice this is not the area because you have this function. You could interpret this as a density of some sort. And if you think mass density, then it's the mass of a plate that is in the shape of whatever this proves to be. Or if you think, you could think of it as a charge density, and so on. So your x is going from minus square root to plus square root. And if you wrote x equals square root and squared, you'd have x squared equals 1 minus y squared. So that what you're talking about is a unit circle again. X squared plus y squared equal 1. So you're going from the left hand to the right with the x. From minus, this minus square root 1 minus y squared is the left hand half of this unit circle. And this is the right hand half. And then your projection on the y-axis is from bottom to top. So it's the whole circle. So your region is the entire unit circle. But it has this variable density of whatever kind. So as I wrote here, this is the entire unit radius circle. So that being so, your r is going to go from the pole to the length of the ray that is what you call the radius, which is 1, and the angle is going 0 to 2 pi. So your new limits then are like this. See, the way you get the limits is you use the xy limits to figure out what the region is, and then say, okay, it's this region. Now, how do I get limits in polar form? You don't try to get from these to these by some sort of substitution in algebra. You just got to picture the region and think it through. And You see, x squared plus y squared is always r squared if you take your pole at the Cartesian coordinate origin. So that's r squared plus 1, and then the dx dy is r dr d theta, because when we went through this, you see, we factored our difference of squares, and this part gives us the r that's over here. And so if that's u, this is half of du, so I did the u substitution and get to here. To do the integral of log u, you have to integrate by parts if you want to write it out. You don't have to write out the integration by parts, because that's Math 175. If you want to go to the back of the book and see that log u integrates to u log u minus u, or you can get it off a graphing calculator, of course Maple. So anyway, integrate by parts, and you get this, and put in your limits, and that gets you down here, and then this is all a constant, and then 0 to 2 pi for the d theta is just going to multiply it by 2 pi. So you end up with that. So the point of this problem is to see that your region is a circle, and then knowing that, you deal that way. Okay, so then the last one, this is actually a very important integral. The reason is that the normal probabilities, the statistics that have anything to do with what living things can do. How long do they live? In the case of people, how much do they earn? How fast can they run? On and on and on. Almost all of the statistics are going to fit the bell curve, as it's called, and this goes back to Gauss. And the integral that you do for what is called the error function, the values are these probabilities, is an integral that looks like this. Now, when you have e to the minus t square, and you don't have any factor of t in there, and you notice you don't, you can't do the thing by parts or use substitution. You have to use something like Simpson's rule. And so in the stats books, inside the front cover, almost guaranteed, you'll find both sides of the inside of the front cover being used to print the numbers in a table, and those are these so-called normal probabilities. And what they are is values of this integral from 0 to various choices for this, and depending on the choice here, you read the value of the integral done by Simpson's rule in the table. Okay, and of course, if you have a, well, of course, there's all kinds of software that does this sort of thing now, and ordinary graphing calculators, I don't think, do the error function, but there probably are statistics calculators that do have it, so on. Well, to be a valid probability function, it has to be that the integral from 0 to infinity is 1. For something to be a probability function, we require that no value is negative, probability is never negative, and that the integration over all possible values is 1. Probability is always a scale between 0 and 1, or as a percent between, like, percent of like the weather forecast probability of rainfall is a percent, but it's 0 to 100%. Okay. Incidentally, they will they will offer the Boise State 360, which is the stats course that the engineering school requires out here next semester. A lady named Elena Velasquez is the lady that's going to teach it. So if you're interested in taking 360, you can take it here in the spring. Well, so the related integral to this, that's the key thing here, would look like this: 0 to infinity, e to the minus x squared. And so we have to be able to get a value for it, and if its value isn't 1, then the square root of that value has to divide our probability integral. Turns out that this integral will be pi over 4, and then 1 over the square root will be 2 over root pi. So you put that in here so that if it were 0 to infinity, the value would be 1. So what we're going to end up with here is using polar coordinates to prove that this thing has a value and to get what it is. So it's something we cannot do in the sense of Math 170, 175. But notice that it is a definite integral, even though it's improper, and therefore it's the same value, if there is one, whether this letter is x or y or z or t or what. So that lets us be tricky. So it's the same value if I wrote it with y, etc. So then the square of this value is the thing times itself, written once with x and once with y. And then we're thinking of this as iterated integral, since the variables are separated, equal to the double integral. That's going in the reverse direction from what we've been doing, where we had the double integral and then we split it up into the two to iterate. So the region then, R, for this double integral, would be the first quadrant, because we'd have x running from 0 to infinity on the x-axis, and y running 0 to infinity on the y-axis. So that gives us if this stick is x and this stick is y, then what you're getting is the first quadrant. So then convert that to polar form in the first quadrant. So the x squared plus y squared, you see this is e to the minus then x squared plus y squared, so it's e to the minus r squared. And then our differential area, instead of dx dy or dy dx, is the r dr d theta. And so then going with the sectors, the r goes from 0 outward indefinitely, so it's out to b, and then take the limit as b goes to infinity. That's going like that. And then the theta goes 0 to pi over 2. So you see, this you can work. e to the minus r squared, because now we have that magic factor of r because of this business, and the r came from the factoring the difference of squares. And so we can do u substitution. If u is r squared, du is 2r dr, so the r dr is du over 2. So that we can put du over 2 there or here. And so then think of the b as a value of u and take the limit of that. So 0 to b, e to the minus u du, and the half is from the u substitution. So you can take the half out. The integral of e to the minus u is minus e to the minus u, 0 to b. And then after you've done all that, you can integrate with respect to theta. And so you have the integral with theta. You have the minus half from the minus in the minus e to the minus u. Limit b goes to infinity, e to the minus b, which is 0, minus e to the 0, which is 1. So the two minuses make the plus, half. And then your integral here is theta, and so you get pi over 2, so you get pi over 4. So the I square is pi over 4, and the I is root pi over 2. So if you multiplied your original integral by 2 over root pi and went through all this, the value would be 1. So that proves that an integral of this type is a valid probability function, which is, to be valid, requires that the integral be 1, integrating over everything that you have. And it turns out, as I said, that the integral is important because the numbers fit, which we've found by experience, fit the probabilities that go with what living things can do. And our vanity is such that we think we're important creatures. Little do we know, right? So this is something that you would see if you take the calculus-based statistics, and it'll be essentially this same kind of presentation, and then you spend the rest of the time working with the probabilities and so on, but this is the basis for it. Well, I think that's enough of this stuff. What we'll do tomorrow now is triple integrals. So one more integral sign. And so it's all the same kind of thing.